I'm not too sure.
Okay, so look at the array on the left, and let's say I want to insert the number 3. How do I do that?
It would have to be in order, correct?
Yeah, so this is ordered. I have to keep the order.
Would it also take log of n?
How would it go? How does it work? So I
Well,
insert the number, yeah, go ahead.
oh, so I would assume you would have to split the array in half and then just keep going until you find uh where 3 would be, like
So far, so
in
good? All
to
right.
make it in order.
Okay, so log n to find where to insert. Okay, so far so good. Now we find that 3 goes here at the beginning. Okay, so
Hmm.
yes, we found it. We took log n time to do that. Now we
Hmm.
have to actually insert it. So insert 3. How long does that take? So first we find, then we insert. Total time is this. We have to find it and then insert it. So this one. Now we have to put 3 in. How does that go? How do we do that?
Um, is it just one step?
So, did I talk about this last class? Hold on, let me go up real quick. I'm sorry. Maybe I erased it. Okay. Anyway. Um, so, no, it's not just one step. Um, this array has like a wall here, okay? You cannot cross this wall. Here, to the right, you can grow. But here is a wall that you can't get past.
Oh, so would you have to ship the entire array over to
Yep.
the right?
Yep.
Okay.
Yeah. So you have to create empty space, yeah. Or shift everything to the right one. Yeah. And how long does that take?
Um, would you have to shift it like one element at a time?
Unless you can think of a better way. I think so. Yeah. Um, mhm.
So it would take uh n steps plus one?
Sure, whatever. N plus one. Or not. I don't know. Whatever. But for here, so this is something that you'd go over in like your first or second class of algorithms. And I'm trying to not make this a class on algorithms, but um, if you want to be very careful, you can do this, and we just have. We've been very careful that first you have to find it, then you have to insert it, and then this other thing. But for large n, this whole thing, log n plus 1, we just call that n, because n is so much bigger. Like when n is some very large number, this term is so much bigger than that one and that one. You can just kind of forget about them. They're noise. So you just find the biggest term and simplify it and just talk about it in terms of that biggest one. So, all right, there's going deeper than I would like. But if you wanted to be careful, yeah, this is called big O notation, actually. So this is O of n. I'm not writing this O, which is very standard because, again, I don't want to make this class too difficult. Okay, very good. So to insert takes time n. Okay, I'm just going to simplify it like that. I'm not going to write this whole thing, which is right. You're correct. That is the careful way of doing it. But to simplify it, we'll just stick with the big one. All right, and to keep things going, thank you very much, I'm going to say that delete is also time n, and I will leave that to you guys as an exercise. We've talked about it before, but if you forget, then try it out. Deletion is also time n. The worst case, again, being if you want to delete the first one. All right. Very good. Now, this is sorting. All right. So here, this is all review, but we're going to be building on this, and so I just wanted to go through it again. You can have an array, and you can sort your numbers in this way. Whenever we're using log, it's base 2, right? Yes. For things computer related, base 2 is sort of assumed. If you wanted to be very strict about it, you can write the base instead of just writing log n. You can write log base 2 of n, but that level of formality isn't required here, and things are just sort of assumed to be the right logarithm.
Sorry, Professor.
Mm-hmm.
Is the base 2 because like the trees could only have 2 like children, or is there any, like, let's say if a tree can have 4, would it then be log 4 to find the search time?
That's correct. Yep.
Okay, let's make sure.
Mm-hmm. Yeah. So I used to wonder if yeah, I mean, if you take a big number, you can have log base 2. If you, that means you break it in half. But yeah, what if you break it into fourths, right? Isn't that faster? Why only go by 2s? Or why not break it into 10 pieces each time? You know, we have 10 fingers and we're used to the number 10, so why not that? And yeah, basically, it's true, but it's not faster by a significant enough amount where you might as well just use base 2. It's the same thing where I was just talking about if you have, you know, log n plus 1, and you just call this whole thing, you just call that n, because, I mean, everything else is noise. Doing here, this is log base 2. If you replace that log with something else, I mean, log base 10, sure, that's a bit smaller, but it's still just going to be dominated by the n. And if it's just a log term, then that's just considered a log function. Whatever base it's in doesn't really matter. At that point, you're thinking more about general properties of any log function, and so it should be true for any log function. And so if you want to choose 2 or 10 or e or whatever, then that's fine. But okay. Yeah, these are interesting details, but yeah, a bit much for this class, I think. What's the difference between log n and log 2n? So here, log n, log 2 of n, this is more formal. This is saying that I'm breaking things in half, or I'm doubling things. I'm working with 2s. Here, they're just not saying what it is. It's assumed that you know what they're talking about. 10 is a common one to have. So like how many digits are in the number 100? 3 digits. That's 10 cubed. I'm sorry, and 1,000 digits. So 10 cubed is 1,000. So log base 10 of 1,000 equals 3. Okay, but you can have different numbers there. So when people leave it off, it's just assumed that you know what it is. It should be obvious, I guess. But if you're being formal, then you should say. And so sometimes people will write this. But in things computers, I feel confident in saying that almost everything is base 2. and people will just say log n. And if you see log n, that means base 2, unless they say otherwise, in which case you can adjust. Okay. Now, okay, I want to continue here. Why do we like trees? Okay, so here we just went through how the data structure of an array with numbers organized in this way, you can have different algorithms. A search algorithm, insert, delete, how long they take, fine. But why do we care about, up here I put a balanced, still a binary tree. The binary here isn't so important, but it's easy to talk about, so that's why we're sticking to it. The balanced is the important thing. Actually, let's take this exact same data from above. 5, no, sorry. Okay. So I'm just taking the same numbers from up here, and I'm instead putting them as they would be in a balanced binary tree. Okay, so everything to the left is always smaller, everything to the right is always bigger, and fine. We're going to look at how long it takes to do each of these. Now in a binary tree, balanced binary tree. So how about Nick?
Hello?
Hey, how long would a binary search take in a balanced binary tree?
Log base 2n.
Base 2 event, sure. Log n. Why log n?
Because the kind of how long or how many kind of nodes are in the tree is 2 to the n.
Yep.
So it would be the inverse to find something there.
By the inverse, you mean the logarithm?
Yeah.
Yeah, right. So he's saying that if you label the number of nodes as something 2 to the n, then in terms of that n, there's n layers, I guess, which would be the log of 2 to the n. That's one way of doing it. If you want to consider the number of nodes and you're counting them as 2 to the n, otherwise, if you want to call the number of nodes n, then it's log n nodes or log n layers, whatever, same thing. Okay, fine. Yeah, so if you have a tree with, okay, we'll just do it real quick. 16 nodes. How many layers does this have?
It would have 4 layers.
4 layers, yeah. So how does it, yeah, what does it look like? Start with that. Okay, and now?
And then another row of 2 children each.
Mm-hmm.
Then one more row of 2 children each.
Good. All right, yeah, technically has one more, but who cares? Yep, very good. And so this is basically log n, right? If you have n nodes, which is 16, then log n, you have 4 layers. Okay, very good. Thank you. How about
You're welcome.
Suraj?
Yes.
Okay. So same thing as
Yeah.
above. Insert 3. Okay, we did this up here, and that took time n. We're going to do the same thing, but now with the binary tree. So insert 3. How does that go?
Would that be just one step?
What's the one step?
Adding the 3 for like under the 5.
So adding the 3 takes one step. How do you know that it goes underneath the 5?
Oh, you would have to go to the 7 first and then the 5. So that would be 2 steps within that.
Right. So like before, when we were being careful, first you have to find where it goes and then insert it.
Mm-hmm.
So, all right. And for a balanced binary tree, well, whatever. Yeah, in the worst case, you're going to be inserting something at the bottom. It's not quite true. Not quite true, but we'll skip past that. Actually, the worst is if you're replacing the root, but it doesn't matter. How long does that take to insert now? If we have n nodes.
Okay. That would be I don't know here. I'm kind of confused.
So here, what I've just written, n nodes has log n layers. Are you comfortable with that?
Yeah. So if there are n nodes, there's 1, 2, 3, right? That'd be 3 layers, right? That there are on this. So that'd be the 4th layer. So it would just be n plus 1, I think.
Well, n here is 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, n is 9.
Oh no. Yeah. Yeah, I'm not sure.
Okay, 8. Number 8. This is 2 to the what power?
That's 2 to the 3rd.
2 to the 3rd. Okay, if I add 1 to that, I get the number 9.
Yeah.
Okay with that? All right, so I'm going to say that this 9 is not any 9. Okay, you can get 9 a lot of ways. 9 can be 10 minus 1. It can be 100 minus 80 or 91. It can be, minus 1 plus 10. 9 can be a lot of things, but this 9 is in particular this 9. Okay, that's how I'm getting to this 9. I'm taking 2 and cubing it and adding 1. Okay, so here, the 3 is the number of layers.
Yes.
So however many number of nodes there are, I'm going to take 2 and raise it to some power and get close enough to it. So here it's 3. That is the log. So here the number of layers is 3 plus 1. But again, like plus 1s, you can just sort of throw them out. Those things don't matter. So if you have... All right. So that is to say that if we have 9 nodes, then we'd have log of 9 layers. And this happens to be 3 point something stuff. A little bigger than 3. So we have 4 layers. All right. So to insert something, if I have a tree with n nodes, this is going to be a really, really big, gigantic tree, okay? I'm not even going to draw it. I'm just going to put ... and then like it's a really big tree with n nodes. How many layers are there?
That'd be log n for layers.
Log n. And now if I'm inserting something in, let's say in the worst case, I've got to go all the way down to the bottom, and then that's where I put the new thing at the bottom. How
Yeah.
how long is the path that I had to take to get there?
So log n would be the layers that there are. So the longest path would be equal to the amount of layers that there are, assuming it goes all the way to the bottom. So that would still be log n, and then you would add 1 because you're inserting whatever number that you want.
I couldn't have said it better myself. Perfect. Yep,
you.
exactly. Yep, very good. So that is log n. All right. Now, to keep things going, thank you very much. Yeah.
Yep.
I will say that delete is a similar exercise that also takes time log n. I won't go through it, but some of you guys, like practice problems and stuff, so there's one. Prove to yourself that deletion takes time log n in the worst case. Now, this is a reason to like trees, right? If we're using an array, cool. If we sort it in this way, we can do search really fast. But insertions and deletes kind of suck. However, if you have a tree, insertions and deletions are pretty fast, and you can search fast too. What's not to love? Okay, so we like trees. We want to use trees. The problem is that the hardware, like in the real world, we're putting data on hardware, and hardware has no internal structure that's like a tree. The internal structure of hardware, I mean, like if you break open any of these and you look at them under a microscope or whatever, the internal structure is like an array, not like a tree or some other data structure. It's basically like an array. But we like trees. So this is now where I'm going to pick up where I left off the last class, showing how you can take a tree and encode it inside of an array. Okay, so here, in the same way that this array is bad for insertion and deletion, when you order things in this way, right, we're ordering them here from smallest to biggest, and you can do that, and it does help with search, but it's not going to work out too well when you're trying to keep it up to date, when you're trying to insert and delete stuff. The tree, on the other hand, is much better for everything. So here, the upper array, the one that's colored, that I'm arguing is a tree. Yes, it's being stored in an array, but it's sorted in a very careful way such that when I look at it, I can see it as a tree. I know that the first thing is going to be the root, and then the next two things are going to be the first layer, then the next four things are going to be the layer after that, and then the next 8 things are going to be the layer after that. And so if I wanted to traverse through the tree, for example, if I wanted to make this path through the tree, 5, let's get a different thing here. Fine. If I wanted to take this path through the tree, 5, 7, 6, right? And I'm going to arrive at 6. I can do that here by, I know that I start at the beginning of the array, now I'm in the root. Now I want to go to the, 6 is bigger than 5, so I should go right. Well, the right child, here, this is going to be the left child, and then here's going to be the right child. So I know if I want to move to the right child, I know where the right child is in the array. Now I'm at 7. And I know that these are 3's children, and these are 7's children. Okay, because of the way that I'm ordering it, I know that about it, and now I can leverage that. So now I'm at 7 here in the array, and 6 is smaller than 7, so I want to go left. I know that I'm at the right child right now in level 1, and so I want to go to my child's left child, and I can end up at 6. The point here isn't the details, right? The details aren't important here. It's the idea, it's the concept that's important, okay? In the same way that I can traverse a tree like the one on the right, I can also traverse through an array. Like I can do that, it's just that you have to organize, your array carefully. And one way of doing that is this so-called layer by layer method. I actually don't want to spend too much time on this method because there's a different method that's actually more important that I'd like to get to. But I think that this is easier getting the point across. How can you take a tree and put it inside of an array? This is one way, this is valid. Like, for example, on the homework, this is fine. Yeah, it works. Let me stop and ask if there's any questions.
Professor?
Yeah.
I'm just wondering, how would you format, like, translate a binary tree to an array? If, say, for example, like on the last layer, say to the right of 8, you put like a 9 in there. So will it just be like null values or like 0 or?
Excellent. Yep. You nailed it. That's exactly what it would be like. Yeah. Let me do that. So yeah, this is a perfect. Yeah, this is a great example. So his question was, what happens? Okay, so fine. We're doing this layer by layer. Now I'm going to insert the number 9. All right. So like, oh, why am I still doing this around 10? Yeah, like what happens if we insert the number 9? Right. Like 9 would go here in the tree. And so now we have to encode this layer, right? So is this to say that, here you have 9 here, and then there's no children, right? I mean, all of these are empty. So, but if we're doing this layer by layer, then these would have to be null. I don't know why that erased. There you go. Yeah, and that's exactly what it would be like. Yep, exactly this. And so this is the drawback of this method, is it can waste space because of these null values. Because yeah, if there's no child there, again, you got to be consistent with your representation. And so you could waste space. The more balanced the tree is, the less space you waste. But, well, one interesting exercise might be to see what this type of tree would look like encoded in this way. How much space is there? Actually, let's do one more. How would this type of tree get encoded into this type of array? And how much space do you waste? This is a bad case, but if the tree is balanced, yeah, this method is actually okay. Doesn't waste so much space. Or should I leave that there? I don't know, maybe somebody wants to take notes or something. Okay. Okay, now I want to get to method 2. And method 2 is going to use pointers. Ooh. Pointers. But I feel like I should go over what pointers are before that. So again, this method 1, the reason why I like it is because it works. I mean, that's so far so good. Yeah, also just sort of, I think it works very well visually, and it gets the idea across of how you can, store a tree inside of an array and not sound like a crazy person. Okay, pointers. We're going to talk a little bit more about the arrays. So here's an array, and I will, I don't know, put in some random numbers. This isn't going to be sorted or anything. Doesn't matter. We're just talking about a generic array. Okay, it doesn't even have to be numbers on the inside. It can be, I don't know, smiley faces. That doesn't matter. But just for a general array, I'll refer to it as A. And it has indexes. Okay, so A, well, let me pick on somebody really quick. How about Zaju? Li Zaju, or Zaju Li. You have a mic?
Yeah.
Yeah, just what I've written here. What is A of 4?
6.
6, very good. All right. What is A of 0?
7.
7. All right, good. Perfect, thank you. All right, so that is the way that arrays work. Now I'm going to create a different kind of an array. I'll call this one array B. And B will also have indices. Should space those out a bit better. Okay. Okay. Here, I'll say this is A by value. Okay. So A is unsorted. And here I want to make the sorted version of A. So Tyler, you have a mic?
Yeah.
Okay, so what is the sorted version of A? I'm taking this array, A, and I just want to create the same array, but now with the numbers sorted.
So in the 0 slot would be -1.
Okay?
Next one would have 3.
Mm-hmm.
Then 6,
Mm-hmm.
7, 8, 9, and then 24.
Perfect. All right. Thank you very much. All right, good. So now that's A sorted by value. Okay. I want to create now another array, A sorted by index. Make this a different color just because why not? Okay. How about Swathi?
Yes. Hi.
Yeah. Do you know what I mean when I say here sorted by index?
Kind of, but not really.
Okay. I love that answer. How about, okay, so if we look at the second array, this number here, this is the smallest number inside of the array A, unsorted.
Yes.
Okay. Now, what is the index of this number inside of A unsorted? Where would
A of
I
2.
find this in A? Very good. Yeah, A of 2. Yeah. There. So there, I'm going to put a 2 here. And so what this means is that this A of 0, this is going to be the index in A of, sorry, A, I'll put it this way, index, A unsorted of smallest number. Okay? So just like that, what does the rest of the array look like?
So 3 would be A of 3,
Mm-hmm.
and then A of 4, A of 5,
Mm-hmm.
A of 6, and then, oh wait, sorry, I missed one. Oh wait, A of 0, and then A of 1.
I have 0, I have 1, okay, yep. And then 3, 4, 5, and what?
0 and 1.
Let's see, so 6 is in position 4. Sorry, I stepped around. So 6 is in the 4th position, 7 is in the 0. No. Sorry, okay, we got to go back. So far, so good. So far, it's good. No, it's still not good. Here, so far, so good. So here, we're writing the number 2 because that's the index in A of the smallest number. Let me write this a little
So
differently.
then,
Oh, go ahead. Yeah.
since 3 is in index 1 in the sorted, the unsorted is index of 3, so the next one would be 3.
Very good. Yes, it's like that. Mm-hmm.
And then 4,
Mm-hmm.
0,
Mm-hmm.
5, 6, and then 1.
Very good. Yes, perfect. Just like that. Okay, very good. Another way you can write this is you could do this. 2, 1, 4, 0, 5, 6, 1. Oh wait. Sorry, that one should be 3. And that one. Good. So you could also how to say this array here and this array here are the same thing. Okay, it's just here I'm drawing arrows to the numbers, and here I'm actually just writing the numbers. So that's index 2, this is index 3, that's index 4. Like that's where the arrow would be pointing. So you can use either way. The picture above is why these are called pointers. I will tend to write things like this, but I don't really care. You can also do it like that, and it's the same thing. The important thing here is, again, the concept of a pointer. So it's something that you hold. I mean, it's like an element of an array, but the way you interpret it is as the index of another array. So the value that's inside of it is the index of a different array. If you don't like the words, just get very comfortable with this picture, and you'll be fine. Okay. I want to go on to now method 2 of representing or encoding a tree in an array. But I want to pause for pointers if you guys have any questions about how they work or what they mean. Okay, then let's go on. I'll take the same tree that I had up above here. Yeah. You know what? In fact, I'll keep the 9 too. That's why not. By the way, really good question. I'm sorry I didn't catch your name, whoever asked about that case. Yeah, that's a really good observation. All right. So now I want to talk about a different way that you can store I got to get rid of the layers because we're doing it differently. All right. Okay, great. Okay, so method 2. Now, we have an array. Okay, so we know that we want to somehow take this picture and come up with some kind of rules that we can follow such that when we're looking at an array, we can recover this. So given an array, we want to be able to reproduce the tree. Okay, this process of if you're given an array and you can reproduce exactly the tree, then that is an encoding of the tree. We've talked about one way, layer by layer. So, here's root, layer 1, layer 2 is going to be a little bit longer, then layer 3 is going to be longer still, and blah, blah. We've shown above that if I give you just this, without looking at the tree, if I give you this array, and I say that is encoded layer by layer for a tree, then you should be able to draw me that tree. Now we're going to do the same thing, but instead of looking at these as layers, we're going to look at them a little bit differently. This is going to have a structure where each node, for each node in tree, we're going to give it 3 blocks. One is going to be the value of the node, and then the index of left child and the index of the right child. All right, that's it. So when we look at this array now, we're going to be breaking it up into chunks of 3. Actually, let me give myself a little bit more room. 324, boy. I think that's okay. All right. So here, when we look at the array, again, we're not looking at it layer by layer like this, where it keeps getting longer and longer, layer by layer. Instead, we're going to be looking at these as chunks of 3 units. Okay, so there's going to be one node. This is going to be some other node. This is going to be some other node. And here is going to be the value of some node. This is going to be the value of another node, and that's going to be the value of another node, and like this. Okay, so because this is an array, I'm going to go ahead and number its indexes. Okay, and I'm going to just start putting things in. Let's say I put the number 7 here, and then we'll have a 5 here. Okay, let's start off with these two. So these first 3, this is going to represent that number. This next 3 here, those 3 are going to represent that number. And let me just put the 3 here as well. So now that 3 is going to be that chunk of 3, which is going to represent that number. Sorry, I'm just getting us off a little bit to a start. So this is going to be the left child and the right child or the index of 7's left child and the index of 7's right child. But I haven't written them yet, so I'll just leave them blank for now. Now the number 5, that we can do. I'll write these in different colors. Let's see.
Professor?
Yes.
For this, why do you want the 7 in the 0 place and the 5 in the 3 place and the 3 in the 6 place? Like, is there any particular reason for why you chose it to be in this sequence?
Yeah, that's a really good question. So I'm doing it should not matter, but I'm doing it here to emphasize the point that it doesn't matter. The 7 being in the beginning here is not important. It could be any number in the tree. The fact that the 7 comes first is irrelevant. Yeah, so that's a benefit of this representation. You don't have to shift things around in the array. You just put things wherever there's space, and in each of these blocks of 3 are unsorted. They can just be in any order you want. And it's the pointers that will fix everything.
Professor,
Yeah.
we're not choosing the meaning like actually saying where the location of the specific number is, because when we insert and delete, the indexes change. So we're doing this because when that happens and insertions and deletions happen, these situations will update with it.
No, that's okay. So yeah, that's another nice thing about this is that it allows you to kind of break the rule that you had before about having to keep everything squished together. Because the problem is if everything isn't squished together, in this case, let's go up here. For this array up top, all of the numbers have to be squished together because you're iterating through an array. And the way that you iterate through an array is you start at the first index, and then you go one by one, every single index. Now, if there's an empty space there, then you'll consider that the end of the array. So if you have an array of 10 elements, then you delete the middle one, and you don't shift everything else over, then when you're reading through the array, you'll go to where you deleted, and then you just say, okay, well, that's the length of the array. I'm done. It's empty.
Right.
And so you have to keep everything smushed together, which is why you get this dumb stuff. But when you're dealing with pointers, it doesn't matter because you're not iterating through this array in a left to right fashion. You start at the beginning, fine, or you have to have a pointer to some node, to the root. In fact, you always need a pointer to the root. Given that, now you have pointers where you can just be jumping around anywhere. If you remove something here and there's an empty space, well, then the pointers are just going to jump past it anyway, so it doesn't matter. That's what makes this better. Mm.
Got it. Thank you.
Yeah. So this is why I think it's good to have like some background knowledge and like getting some idea of like the way that things work on hardware. I mean, otherwise, like, why do these things exist? But yeah, there's benefits to these, so that's why we're going through it. Can you switch the 7 and the 5? You could. Why can't 5 go first? It could. But if it does, it should be an accident. It's a feature that these things don't have to be organized. That's a good thing. Because that way you don't have to keep it organized. So it saves time. Yeah, if you're given a tree like this, but if you're given a full tree, sure, you can organize it in some way you like. But now if you imagine inserting, deleting, inserting, deletion, deletion, insert, and now the tree can get all jumbled up. And you can just tack things on at the end, or like wherever there's free space, that's where the thing goes. You don't have to worry about maintaining the order and shifting things around, and because the order isn't in their locations in the array, you're traversing the tree through pointers, like through taking portals to different locations. So when you're traversing a tree that's encoded in this way, let's say, okay. If you sort numbers from small to big, 0, 1, 2, 3, 4, 5, 6, and like this, then you have to traverse the array. Okay, well, no, I'm sorry, you don't have to necessarily do that, but let's say that it's an unsorted array. No, whatever, it's sorted. Fine. Then the way that your binary search would work is, or let's say, what do I want to say? For your standard array, when you're traversing it, you need to go one by one. When you have the layer by layer method, these sizes keep getting increasingly large. In fact, it's not a very good one. This should be much larger. Right? Because here's layer 1 with 1 node. Now here you have to have 2 nodes. Then here you have 4 nodes. Then here you have 8, then 16, and on and on. So when you're traversing this, you're each time jumping to the next layer. So this is a lot faster because you're able to skip huge parts of the array. Fine. Now, if you're traversing the array with pointers, I mean, you might start here, and then you go here, and then you jump over here, and now you jump over here, and then here, and, you're just sort of jumping around all over the place. which is okay. You can do that because you have pointers. So you don't get lost. You never reach empty space that shouldn't be there. Everything is just stored in a pointer. And this way, this last way, is actually what we're going to be building on more. So that's why I'm trying to emphasize it a bit more. Okay, look, so we don't have that much time left, but I do want to finish or get a little bit further along in this thing up above, if you're taking notes or something. So let me just go up here. All right. So here, again, it's a feature that these nodes can be out of order, and it doesn't matter. If you want it in order, go ahead, but make sure that you're not enforcing that order, because then you're going to be wasting time doing something that you don't need to do. Here, things can be in whatever order, and whatever order they're in is fine. So, yeah, if it's in small to high order by value, maybe, but that's an accident. It's not wrong, but okay. So that's why I'm putting the 7 in the beginning, to emphasize that point. Having the 7 in the beginning makes this no different than if 5 came in the beginning and then 7 and then 3. Doesn't matter. So I'm going to keep it this way to emphasize that. Now, for 5, here, pointers can also point to the arrays themselves. So here, 5's right child is the number 3, and 3 is at position 6. So that's the number 6. Okay, so it's a pointer to the array itself. Its right child is the number 7, and that's in position 0. So that's the number 0. Okay, if you want to use the arrows, if you want to use the numbers, I don't care. You don't have to use both. I'm just using both because I would normally just write the numbers. Now, let me see. 6, 8, 4, 1, 9. All right, so let's finish up with, I'll pick on one student. How about Karnik? You can wrap us up here.
Can you hear me?
Yes, I can.
So where would 9 go?
So I all of these empty spaces, maybe we can just go from like left to right. You can just tell me what to write.
Okay. So for 7, the index of left child, would that be 6? Like would the child be 6 and 8 or?
Yeah, so it's this one. 6 is its left child.
So you can write 9 and 12.
And then 2. Let's see, then 8, 12. Yep. Very good. All right.
For 3, it'll be 1 and 4. So you can write 18 and 15.
Yeah. Okay.
For 6, it'll be.
Oh, here. Good point. Null and null.
Okay.
Yeah. So if you have no, if you don't have a child, you just put null there. Okay. Good. Actually, let's stop there because we're already at the end of class, and now that leaves everyone else to finish up this array, and see if you can finish it. That's good practice. Okay. Well. Yeah, thank you guys. And class is over. Good luck on the homework. And I will see you on Friday.
Hello, Professor?
Yeah.
Yeah, so I just had a couple questions. So my first question is,